Hi there, welcome to today's video. Today we are going to study the second paper for speech to unit translation. So I'll go back to the paper that we studied in the last video to just briefly touch upon where we left off, and then we'll come back to this paper and understand what are the contributions of this paper. So in the last video we went through this paper called direct speech to speech translation with discrete units. Discrete units is the key here. So what this model for direct speech-to-speech translation does is it first applies HuBERT to convert the continuous speech of the target language into discrete units, and then it applies a transformer-based model for translation of the speech from one language to another language. So this is what we studied in this paper. Now, these same set of authors or similar set of authors from Facebook, they came up with the second paper called Textless Speech-to-Speech Translation on Real Data. So the key here is on real data. So in the previous paper, the experiments that were conducted were on a Fisher dataset, which is a Spanish to English dataset, and the data set is not all real data. Some of the data there is synthetic data that is generated by text-to-speech systems. So here, the key is that they want to be able to apply this speech-to-unit translation, which was presented in this previous paper, on a real data. So that's the key. So what are the contributions of this paper? So this paper, again, it is the first speech-to-speech translation system that is trained on real speech-to-speach translation data. And that data that they use during the experiments is called Vox Populi datasets. And they are doing the translations for English to Spanish, Spanish to English, English to French, French to English. So those are the pairs that they are showing the experiments on. The main contribution of this paper is a novel technique for speech normalization. And we will spend most of the time understanding what this speech normalization technique is and why it's important. And then the other thing is, because they are using more than one language pair, they also trained the HuBERT model, which we are now familiar with, on multiple languages, and that's called multilingual HuBERT. Finally, after doing the speech normalization and training the HuBERT with multiple languages, the rest of the task, which is to translate from one language to the other language, is still done with the same model called speech-to-unit translation model that is presented in the first paper. When I say the same model, I mean the structure is the same. However, they did change the dimensions for the parameters of the model. For example, the number of encoder layers, the decoder layers, and stuff like that. But the structure of the model is still the same. Okay, now let's get into the details of what this speech normalization technique is and how they apply it. So the speech normalization technique that is presented here is a self-supervised unit-based. We know what is self-supervised and unit-based. Basically, whenever you see the word unit-based in context of speech processing, all it really means is that we have converted the continuous speech input to a discrete input, and that's where the word discrete unit comes from, and that's what this unit is. It's a discrete unit-based technique. So once again, in this work, the authors extend the speech-to-speech translation setup that was presented in the other paper that we just saw, and they apply it in the real-world data without the use of any text or phoneme data for training. So why is this speech normalization important? When we have the data from different speakers collected in different recording environment, that data usually has a lot of variation. So this speech normalization, it helps to minimize those variations, and this helps to get better performance out of the speech-to-speech translation model. So that's the basic idea why speech normalization is needed. Now I think we're ready to get into the details of what this speech normalization technique is. In this diagram, the authors are trying to illustrate what the speech normalization technique is and how they train this speech normalizer. I have jotted down some of the steps here, but before I go through them, I think it's good to have a high-level understanding of what we are trying to get here. So let's take a moment to understand, to get a high-level picture. So what we're trying to get to is we have a speech-to-speech translation task. So that's the main goal. So let's take an example of one translation pair. So let's say we're trying to go from Spanish to English. So we have a bunch of audio pairs in these two languages. So we have sentence 1 in Spanish, sentence 1 translated in English, sentence 2 in Spanish, sentence 2 is translated in English. So we have a bunch of those pairs. And here the source language is Spanish and English is our target language. For the speech to unit translation model that was discussed in the previous video, we want to predict the units or the discrete unit in the target language. So the first thing is that for the target language, we want to generate these discrete units. And in order to create these discrete units, we use the HuBERT model. Remember, in the original data set, this English language, even the Spanish, but this English language is going to have examples from multiple speakers, right? So we have sentence 1, sentence 2, sentence 3, sentence 4, again sentence 1, sentence 2, sentence 3, sentence 4. These are all in Spanish and these are all in English. So for this English language, these examples, 4 different examples from our data set, they are from different speakers. So they have a lot of variations amongst because they're from different speakers, different recording environments, and that's what we're trying to normalize. So this speech normalization technique that is presented here is applied on this target language. That's the key. Now, how do we do the normalization? That's what we're going to spend most of the time now. Let's go through the steps here. So in order to train this speech normalizer that they're presenting here, the first thing is how do we create a data set to train such a model? So the data set that we need here is we need pairs of audios from random speakers and one reference speaker speaking the same content. So one more time. So remember how we were looking at the example from speech-to-speech translation dataset just a moment ago. So let's take an example again. So let's say you have the English dataset. This is our target language, and here you have several sentences, right? So these are different inputs in our dataset. So sentence 1, sentence 2, sentence 3, sentence 4, and these are spoken by different speakers. In order to train the speech normalizer, the dataset that we need is we need one reference speaker. So we have, let's say I am gonna create a dataset, me being a reference speaker. So I will have to have a dataset that, let's say the reference speaker is called speaker 0. So whatever the sentence 1, sentence 2, sentence 3, sentence 4 is spoken by all these 4 different speakers. I need my reference speaker to also speak the same sentences. So now I have 4 sentences, and for those 4 sentences, I have pair of audios from random speaker and a reference speaker. Random speaker, reference speaker, random speaker, reference speaker. So this is the kind of data set that we need in order to train the speech normalizer. Okay, so let's start the training process. So what we do is, the first step here is we take the data from the reference speaker alone, we pass it through the pre-trained HuBERT, and what is this gonna give us is the discrete unit. Remember, the HuBERT model, all it does is it converts this continuous speech into discrete units. So that's all we are doing here. We are taking the data from this single reference speaker that we just were talking about. We pass it through the pre-trained HuBERT, and this gives us the discrete units for that reference speaker. And these discrete units that are generated from the speech of the reference speaker are called original unit or orig unit. And then next we start training the speech normalizer, or I should say what this speech normalizer is. It's basically we fine-tune this pre-trained HuBERT to create this speech normalizer. And this fine-tuning is done with this parallel dataset that we just talked about. The parallel dataset that contains the sentences, same sentences spoken by random speakers and the reference speaker. So that is the dataset that goes in here for training. So when we train it, we need the labels, right? This is common for all kinds of supervised training. So for supervised training, we have the inputs and then we have the labels associated with each input. So in this case, the input for training is the speech from the random speaker, and the out or the label, the target for that particular input is the discrete unit of the same sentence from the reference speaker. So remember, we created this data set. So this data set is going to contain speech from the multiple speakers, speaker 1, speaker 2, speaker 3, speaker 4, speaker 5 for different sentences. And this is your same sentence spoken by the reference speaker. So the first thing that we have done is for this reference speaker, we have converted this continuous speech into discrete units, and these discrete units are called original unit or orig unit. Now, these original units become the target for fine-tuning, which is the second thing here. Now you might ask, not really, because here the target, it says reduce original unit. So what that really is, so for the original unit, from the original unit, we create this reduced unit, and the way it's produced is, so basically, wherever you have the original units being repeated, they just remove the redundancy. So for example, here the sequence of original unit is 33, 93, 93, 444. But when we create the reduced unit from this, so you will have 33, but then since you have 2 times 93, they just keep it 1 time. Again, you have 4 being repeated 3 times, they just keep it once. So that's what the reduced unit is, which is produced from the original unit. Okay, so these are your targets for fine-tuning this HuBERT model with the parallel data set that we just created. Now, once we have fine-tuned this HuBERT model, now this speech normalizer is ready to be used for any downstream tasks. In this case, downstream task is nothing but the translation task that we always wanted to achieve. Okay, let me see if I covered everything that I wanted to. So again, the first step is we create a data set by using a pair of audios from a random speaker and a reference speaker speaking the same content in the target language. And then we apply HuBERT So the first thing is we apply HuBERT on the reference speaker to create this discrete units, which we call original unit or orig unit. These original units, they are used to create labels or targets for training a speech normalizer, which is nothing but fine-tuning the HuBERT model. Then we proceed with training the speech normalizer, and then finally the speech normalizer that is trained can be used for downstream tasks. So this completes the speech normalization aspect of this paper. Okay, here I'm just showing again what the data set for the speech normalization looks like. We talked about it, but just briefly saying again. So we have multiple sentences, and those sentences are spoken by different speakers. For speech normalizer, what we need to do is we need to create this data set where you have the sentences spoken by different speakers, also spoken by the reference speaker, which in this case I call S0. Now, let's look at the overall speech-to-speech translation model and how the speech normalization is used. The speech-to-speech translation model is the same that was used, created in the other paper that we studied in the last video. So we will not go into the details of that model, but we will see how the speech normalization plays a role here. So this speech-to-speech translation model is a speech-to-unit translation model. So what it takes is, it takes the input speech of the source in the source language. So in this case, we're going from Spanish to English. So here you have the speech in Spanish, which is input to the model for the translation model, and the target or the labels are the discrete units of the target language. So these discrete units, these are generated from the speech normalization process. Now, if you compare this to the previous paper, these discrete units were produced by the HuBERT model, by the pre-trained HuBERT model. In this specific paper, the improvement is that we are creating this discrete unit not by a simple HuBERT pre-trained model, but we are creating this speech normalization technique, which is based on the HuBERT model, but we fine-tune that HuBERT model. So these discrete units are created by the fine-tuned HuBERT model, which is called speech normalizer. So these are the targets for a particular speech input in the Spanish language. So then we train this speech to unit translation model for translations. And then finally, we have the vocoder, which converts this discrete units into the waveform so that we can hear the translated speech. So in nutshell, if we have to summarize this, there are three things that are going on here. So first, we use the speech normalizer to give us the discrete units, which are called normalized unit for the target speech. And this becomes the target for the speech to unit translation model when we are training it. And then the second thing is we train the speech to unit translation model with these normalized units that we just created using a speech normalization process. And finally, we apply the vocoder to convert the discrete unit that are predicted by the speech to unit translation model to convert the discrete unit to the waveform so that we can hear the speech. Now, this entire thing is for the training. But when we use this model, speech to unit translation model for inference, all we need is we just need this and this, the gray portions or the blue portions, I guess. So we are going to, during the inference, we're going to give it the source speech, and then this model is going to predict the discrete unit in target language, which in our example is English. And then we take the discrete units that are predicted by this model of English language, and we pass those discrete units to the vocoder, which is trained separately, and then this vocoder converts those discrete units into a waveform, and then we can hear the translated speech in English. So that's the overall model here. So now let's go to there are several experiments. Again, when I do these videos, I usually skip the experiments, which is not a good practice. I mean, I personally read the experiments. They are very important, and that's really required when we publish a paper. But I intentionally leave those out because for the videos, because my main goal is to highlight what is the model and how we go from one paper to the other paper. So that's my main goal. That's why I'm skipping the experiments. But for you, if you are in this domain and you are researching on this topic, then experiments become really important. Please read through the paper. So I'm just going to go to the conclusion here and try to summarize what we just learned. So in this paper, the authors present a speech-to-speech translation model, which is trained on the real-world data. The real-world data that is used here is Vox Populi dataset, and the main contribution of this paper is the speech normalization process. The speech normalization process, as we talked about, is based on fine-tuning a HuBERT model. The authors show through their experiments that applying this speech normalization really improves the performance and effectiveness of the speech-to-unit translation model that was presented in the previous paper. So I will stop here, and there is one more paper or one more improvement that the authors made to this overall technique, and I will present that in the next video. With that, thank you for listening, and I hope you have a good day.